Ever wondered how scientists map the Earth's inner workings? It's not like, digging a giant hole.
Nope, not exactly. They use seismic waves, like ripples from earthquakes.
Ripples, so like dropping a pebble in a pond?
Exactly, but these ripples travel through the Earth, and how they travel tells us about what's inside.
And this paper uses AI to analyze those ripples, right? Pretty cool. So this SfNet thing, it's all about using deep learning to analyze seismic surface waves, right?
That's the core idea. Traditional methods for seismic inversion are slow and can get stuck in local minima. Deep learning offers a faster, more robust solution.
Like finding the best route on a map, but instead of a city, it's the Earth's interior?
Precisely. And deep learning can explore the map much more efficiently.
This SfNet, it's a convolutional neural network, right? What's that all about?
It's a type of artificial neural network that's really good at identifying patterns in data. Think of it as a superpowered image recognition system, but for a seismic wave.
So it's learning to recognize the patterns in the waves that tell us about the Earth's structure.
Exactly. It learns to associate specific wave patterns with specific subsurface structures.
Training a neural network needs a lot of data, right? How did they get that?
They cleverly used synthetic data. Instead of relying on real-world measurements, which can be expensive and time-consuming to acquire, they generated thousands of synthetic models.
Synthetic models, like computer-generated versions of the Earth's interior?
Yes, they created a wide range of possible models and then calculated the corresponding seismic wave patterns. This created a massive training dataset.
Smart. So the network learns from these simulated scenarios. The paper also mentions a random sampling strategy. What's that all about?
Traditional deep learning methods for this kind of problem often require very specific data sample. This limits their applicability. Their random sampling makes the method more flexible.
So it's more adaptable to real-world data, even if it's not perfectly sampled?
Exactly. It makes the method more robust and easier to use.
How does SfNet compare to the traditional methods?
They tested it against a neighborhood algorithm, a common nonlinear inversion method. SfNet was significantly faster and more accurate.
Faster and more accurate? That's a pretty big deal in science.
It is. The speed increase is particularly important when dealing with large data sets.
So they applied this to the Chinese mainland. What do they find?
They created a new reference velocity model, China versus DL 1.0, which showed better fits to the observed data than the traditional method.
So a more accurate picture of the Earth's structure beneath China?
Precisely. And this new model reveals important details about the region's complex geology.
They also experimented with different network architectures, right?
Yes, they tweaked various parameters to optimize the network's performance. They found that a certain level of complexity was optimal. Too simple, and it couldn't learn the patterns well enough. Too complex, and it overfit the training data.
Like Goldilocks and the Three Bears, but for neural networks?
Exactly.
And the size of the training dataset also matters, right?
Absolutely. They tested different dataset sizes and found that a certain size was sufficient to capture the diversity of possible Earth structures. More data didn't necessarily lead to better results.
So there's a sweet spot for data size as well?
Yes, a balance between sufficient diversity and computational cost.
So how widely applicable is this SfNet method?
It's designed for surface waves in a specific period range, but the network can be retrained for other ranges. The authors even provide examples of this.
So it's a flexible tool that can be adapted to different regions and datasets?
Exactly. It's a powerful new tool for seismic imaging.
So to summarize, SfNet is faster, more accurate, and more adaptable than traditional methods?
Yes, it leverages the power of deep learning to efficiently analyze seismic data, providing a more accurate and detailed picture of the Earth's subsurface structure.
And it's all open source, right? So other scientists can use it. The data and the model are available online, right? So other researchers can build on this work?
Yes, the authors have made their data and software publicly available, encouraging further research and development in this area. This is crucial for the advancement of the field.
So this deep learning approach to seismic imaging is a game changer, offering a faster, more accurate, and more adaptable way to understand the Earth's interior.
Absolutely. It's a testament to the power of combining advanced computational techniques with traditional geophysical methods.
That was a great discussion. Thanks for sharing your expertise.